Hello everyone, today I'm going to present our team's work accepted at ICCV 2025, WildSeg3D, segment any 3D objects in the wild from 2D images. Background: implicit representation-based 3D segmentation. Problems with nerf reconstruction for each scene requires training a neural network to obtain prior knowledge of the neural radiance field, resulting in prolonged training times. In neural network implicit reconstruction, rendering from each viewpoint necessitates forward propagation, resulting in low time efficiency. Explicit representation-based 3D segmentation. 3D Gaussian splatting advantage utilizes Gaussians to explicitly store object geometry and color information, enabling fast rendering of Gaussians through rasterization technology. Disadvantage: Gaussian components still require pre-training for each scene, 10 to 20 minutes, lacking generalization capability for reconstruction across different scenes. Motivation and contributions of this paper. Motivation. First, NERF-based and 3DGS-based 3D segmentation models require pre-training on specific scenes during target reconstruction segmentation before performing the 3D segmentation task, which does not satisfy the demand for rapid segmentation. White right-pointing backhand index, a solution enabling fast segmentation, is proposed. Second reconstruction via mask 3 suffers from insufficient accuracy when aligning 3D point clouds from multiple views, causing blurred details and inconsistencies in partial view reconstructions. White right-pointing backhand index, the alignment iteration scheme, is revised to enhance accuracy. Contributions of this paper. Mask cache, introducing SAM2 as a pre-processing module to construct a feature cache that stores all objects associated segmentation masks across all viewpoints. We propose the Dynamic Global Aligning (DGA) method, which introduces soft masks to minimize background interference and dynamically adjusts aligning weights. This adjustment enhances the focus on challenging sample points, thus improving the overall alignment effectiveness for the target objects. We further introduce Multi-View Group Mapping (MGM), which combines the mask cache with the DGA strategy to integrate multi-view segmentation results into an aligned global coordinate system. Step 1. By leveraging the video tracking capabilities of SAM2, we perform panoptic segmentation on a single viewpoint, generating precise masks for each target object within the scene. These object masks are then stored offline in the mask cache, creating a repository of segmentation data that can be efficiently accessed during real-time processing. Step 2. We introduce Dynamic Global Alignment (DGA), a method that dynamically adjusts attention on view-specific points during matching, minimizing alignment errors during the global registration of point maps across multiple views. Step 3. The MGM module retrieves target feature points from the mask cache based on user inputs and generates a unified 3D mask for the target across all viewpoints in real time. Qualitative results. Visualization on the NVOS dataset. A-D show the sparse view reconstruction and timing results on horns, treks, orchids, and fortress scenes, including pre-processing and DGA-based scene reconstruction. Target objects for segmentation are marked with red dashed lines in the first column. From left to right, segmentation results and elapsed time from prompt input to segmentation acquisition across models. Quantitative results on NVOS dataset. We compare the performance of our WildSeg3D framework against other state-of-the-art methods. WildSeg3D outperforms existing approaches in both MIOU and MACC. In terms of runtime efficiency, NERF-based methods, including NVOS, SGI-SRF, and SA3D, as well as 3DGS-based methods such as Saga, OmniSeg3D, and FlashSplat, typically require scene-specific training. Quantitative results on SPNNERF dataset. In comparison to MVSeg and SA3D, our method achieves comparable accuracy while requiring only a fraction, approximately 1/10,000th, of the processing time. Moreover, when compared to Saga, our approach not only demonstrates superior accuracy but also outperforms Saga in terms of processing time. Overall, our method delivers exceptional performance, making real-time intuitive 3D segmentation feasible in practical applications. Ablation studies. To further validate the effectiveness of DGA, we also integrate it into Dust3R, replacing the matching maps with SIFT. As shown in table, incorporating DGA significantly improves performance in both Dust3R and Mask3R models compared to traditional GA training methods. This table presents an ablation study on the number of viewpoints input into WildSeg3D. Considering overall performance, we randomly select 5 viewpoints in prior experiments on the SPNNERF dataset, our method outperforms WildSeg3D when 7 viewpoints are selected. Conclusion: 1. We introduce WildSeg3D, a feed-forward method that enables real-time intuitive 3D segmentation from 2D images without scene-specific pre-training. 2. With dynamic global aligning, WildSeg3D learns high-quality transform matrix for each view, aligning 2D images to an aligned coordinate system. 3. Additionally, mask cache stores masks from multiple views consistently. 4. Real-time intuitive segmentation. MGM uses a search strategy to retrieve target masks and map them into an aligned 3D space, responding promptly to user inputs. For dot-through experiments, WildSeg3D demonstrates a significant speed-up over existing methods while maintaining high accuracy. Future work. 1. SAM2's 2D segmentation has limitations in tracking small targets and objects with similar appearances, and our method consequently faces these challenges. To address this, semantic embedding of point clouds in 3D may be a future direction. 2. Although we successfully integrate 3D reconstruction and segmentation into a single pipeline, it is not strictly end-to-end differentiable. Therefore, feed-forward semantic reconstruction is also a topic worth exploring. Thank you for your attention.